suppose we have a vector A1, A2. I have an x coordinate, I have a y coordinate. And we all know, hopefully, what polar coordinates are. Okay. We did take pre-count this one a long time ago. So in the 2D space, if I have a point x comma y, I can write x in terms of an angle. I can write y in terms of an angle. How?
Isn't x r cosine theta, isn't y r sine theta?
Is it?
I think so.
Chase thing that x is simply r cosine theta, y r sine theta. Agree. What is theta? The angle. What is r?
The magnitude of the length.
Radius, right? When we get to the magnitude. Radius. So r is the radius of whatever circle you are representing. So we have the unit radius, and then we keep on putting circles. So the magnitude will change, but the direction is not going to change. Agreed? In terms of x and y, what is r?
A1.
Let's get practice. In terms of x and y, using these two, what is r?
The square root of x squared plus y squared.
Square root of x squared plus y squared, but why?
Just, I don't know, I didn't think it that way, someone told me.
Someone told you.
Well,
There's a
Pythagorean theorem or something.
Pythagorean theorem or something? It is Pythagorean theorem. As I mentioned, everything goes back to that guy. R squared is x squared plus y squared. You should know this because we covered it here. That is the equation of a circle, right? Which would mean r the square root of x squared plus y squared, all in polar system. Okay. I can draw a circle properly, but watch me mess up. Not bad. No, it is bad. Sounds bigger than that. I'm no artist. So if I pick a point, P, call it XY, radius R. Good, center. Yes, and Pythagorean theorem, you would get x squared plus y squared equal to r squared. But as the angle of theta with respect to your reference axis, which is this. That makes it fun. Okay, so x is r cosine theta, y is r sine theta. Where do they come from? From that. I'm going to look at a vector space. Instead of x and y, I have a1, a2. So good. I'm referring to the same form. R is the square root of x squared y squared. So here I will have something of this sort. Agreed. But what is that?
Magnitude of vector A.
Magnitude of vector A. Do we agree? Yes. Now, this entire thing, when you find the angle, we know the radius can change, but the angle doesn't change. When we find that angle, what circle do we use? We have the circle, but typically we go for one specific circle that has a name, a unit circle. In other words, the radius of that circle has to be one. If you have that equation and you want a unit circle, what would you do?
Just x squared plus y squared equals 1. Like,
It's like arbitrary. Just because you feel like it.
that's the equation of the unit circle.
That's
all
what
you're
we're
asking.
radius one.
True, but I want to transform algebraically to one. Radius has to be one. What should I do?
Let r equal 1. This is what.
Algebraically, Chris, not to make r equals one.
R squared.
Thank you. What's your name?
Cut.
Carl? Tom.
No, cut.
Carl. Okay. Divide by r squared. So one would be x squared over r squared. Y squared over r squared. Yes. Which in this case I can rewrite as a1 squared divided by the magnitude of a1 squared. Agreed? Oops. Plus comma a2 squared divided by magnitude of a2 squared. Yes, no, maybe. But a magnitude of the vector a. So I pretty much took that vector, divided by that. Now, going back to what I started with, I'm going to argue that's simply the unit vector corresponding to vector A. Do you agree? So I had V, VU. So in this case, how do I get the unit vector corresponding to A? I simply divide by the magnitude. So I'd have A1 divided by the magnitude of A, I vector, plus A2 divided by the magnitude of A, J vector. Yes. In that case, I will simply get that component, you square, I have that. That component, if you square, I'll have that. So if you want to make a one-to-one connection with the unit circle, we simply divide by the magnitude. Got me so far? Mind you, doesn't change the direction. It only changes the magnitude. Good so far. Now, whatever theta I have here, I can move it over here. Good. Now that we're going to get into 3D and all, instead of theta, I'm going to call it alpha. Good. We have y to be sine theta. But if I started the y-axis and came this way, what would that angle be?
Whatever that angle is minus 90,
Okay, 90 minus,
or wait, yeah, 90 minus whatever,
K, no, A.
Matthew.
Well, IJK and then still there. 90 minus theta, complementary angle. So this is 90 degrees minus theta. And I'll call that beta. Good. If I look at the vector from the y-axis, then it'll be 90 minus theta, which will simply be the complementary angle to theta. Can I erase this part? Great. I started the lecture by saying directional cosines. Well, that's a sign. And that's not a good sign. Because I want a cosine. So how do we go from here to a cosine?
Go on a tangent,
Huh?
go on a tangent.
Go on a tangent? I don't want to go on a tangent.
Oh, okay. That was a joke.
Mine was a joke too, you just didn't get it.
I get it. Never mind.
You take a derivative,
Okay, trigonometry.
Wait, what are we?
y is equal to r cosine of 90 minus theta.
Very good. So this is simply r cosine 90 degrees minus theta. Rachel, did you say something?
Oh, I was trying to figure, I forgot what we were looking for to begin with, it's okay. We're
Well,
looking
maybe-
for that angle right now.
This one or this one? So with
90
respect to
minus
this
theta.
axis, we would have x to be r cosine theta, y to be r sine theta. But if I start looking at the individual components with respect to their own axis, this one is theta, that's 90 minus theta. I can change that and rewrite it as r cosine alpha, so great. R cosine, cosine of beta, agreed. I already made the connection between R from polar to over here, regular 2D space. What is R corresponding to that vector?
The magnitude vector.
The magnitude of the vector, and I wanted to
Oh, one.
1. And when would that happen? I want R equals 1. Yes? I did it over there, and Chris said, oh, simply change R by 1. Right, and I said, that's way too easy, I don't want that. So I did an operation. What is that operation? I divided both sides by r squared, which over here translated to dividing that vector by its magnitude. Yes, so I will get that r to be 1 if x component a1 divided by its by the magnitude of the vector a. Good. And that would equal cosine alpha. Yes. So starting with the x component, here I have r cosine alpha. I don't want r, r1 has to be 1. And how did I achieve that? Here, divided by r squared, vector notation, divided by the magnitude. So now, under the case where I have unit vectors, the x component is that, and I have cosine alpha. Good.
Is the y supposed to be r sine 90 minus theta? Or is that, why does it change?
Trigonometry. What is cosine 90 minus theta? Sine theta. We do agree, right?
Yeah.
We'll go back to sine cosine, 90 minus theta is the complementary angle. Easier way to remember. We say cosecant, cotangent, cosine. What does the cos stand for? Complementary. So we call it cosine because it's complement to sine. Okay, I got the x component. What should the y component be if I follow the exact same logic? Chase.
A2 over the magnitude of A is equal to cosine of theta.
A2 divided by the magnitude of A, which would equal to cosine of beta. Yes. So cosine of alpha, cosine of beta. Good. Now, since day one, I've been saying, well, whatever happens in 1D or 2D applies to 1D, applies to 3D, applies to 4D. That's the beauty of math. How did we go from vector A1, A2 in 2 dimension to vector A1, A2? No, vector A in 2 dimension to vector A in 3 dimension.
Add another component.
Just another component. So that was our standard notation, X, Y, Z. I have some 3D point. Just add another component relative to the origin. Let's just say it's somewhere in space. My brain is going ahead of me. How did we come up with the directional cosines in 2D? So we got the directional cosines by looking at the reference axis. We got alpha in reference to the x-axis. We converted sine to cosine by looking at the reference axis to be 1. Instead of looking at it this way, you're looking at it that way. Doesn't connect. So if I want a directional cosine in 3 dimensions, the first component I must be looking at, or looking at that point with reference to the x-axis. Agreed? So start at x. alpha. Good. If I want to look at beta, which in 2-dimension, second component, the y component, how did I get that? Well, I started at y, came back this way towards the vector. So where should I start? Here, there.
Right side.
On. Do we agree with Chase? Beta. Good. That leaves me with one option. What is that one option? Does that axis? So with respect to Z, going to come this way. Typically, we call that gamma.
Call what?
Gamma.
Oh.
Gamma.
Yeah.
Gamma. So alpha, beta, gamma. Great. Let's see if you can use logical deduction. Based on what we know, what is cosine alpha? In 3 dimensions.
Should still be a sub 1 over the magnitude of a.
Okay. What is cosine beta?
A sub 2 over the magnitude of a.
Are we agreeing with Chris? Okay, that leaves us with cosine of gamma.
And I'm gonna take a wild guess and say that that's a sub 3 over the magnitude of a.
Pretty wild, right?
Yeah, I know.
Good. Cosine of alpha is simply a1 over magnitude of a, a2 over magnitude of a, a3 over magnitude of a. So those are simply the directional cosines in 3 dimensions. With me? You don't have to memorize these if you understand what's going on. And I started with a very simple case, which is 2D. I could have started with 1D, but didn't. With me? So you can see how I went from the polar expression and then related it to a unit circle, because that's how we came to the conclusion that x has to be cosine theta, y has to be sine theta. And I related that to a vector, but the vector has to have a magnitude of 1, so we need a unit vector. So I divided each component by its total magnitude. I didn't want to commit any sins, even though I love them. Are you awake? I'm trying to prep you for this seminar that's coming up. So I didn't want to have sine, so I wanted to write it in terms of cosine, cosine 90 minus theta, which would simply mean I'm changing the reference axis. I'm making it in reference to y. So pretty much alpha, beta, gamma are angles that the vector forms here in 3 dimensions with respect to its own axis. Good. And you can get it provided they have unit magnitude. Before we end, why unit magnitude? Who the hell cares? Why do we go to the unit circle when we talk about cosines and sines?
Is the sine curve only goes up
Now then, Rachel,
Sine curve only travels one,
travels one,
like, I don't know, it only like.
what do you call this? I mean, that's sine,
Yeah.
I see what you're saying, I just want the right words.
Period.
Period is magnitude of one, basic algebra, what do you call it? Starts with the letter R, ends with the letter E. It's a 5-letter word,
Range.
range. -1 to 1, which is why we normalize it and make sure that magnitude is 1, or else you can't find that out. Sure, you can extend this to 4 dimensions if you use logical deduction. Let's say, what is the next one? Alpha, beta, gamma, delta. Cosine of delta, what should it be?
A sub 4 over the magnitude of A.
A sub 4 divided by the magnitude of A. But good luck visualizing that fourth element. Yes, so this is the best we can go, and if you want to extend, you can extend this to any dimension. Do we follow? Okay. I will do a problem on this next time.